In the boundless expanse of space, stars are born, blaze with light, and inevitably die. But for the most massive among them, death is not an end. It is a profound transformation. A star that once lit up the night sky can, in its final moments, collapse into something vastly more extreme, more mysterious, and more compact than our imaginations have yet fully grasped. This is the story of the neutron star, a stellar remnant so dense, so powerful, so fundamentally alien, that even a single spoonful of its material defies our physical understanding. It is, quite literally, the incredible shrinking star, a gravitational miracle compressed into just a few short kilometers, yet possessing the mass of an entire sun. We begin at the height of a star's life. A massive star, at least 8 times the mass of our sun, spends millions of years in a delicate balance between gravity pulling inward and fusion pushing outward. Deep in its core, atomic nuclei collide with such force that hydrogen fuses into helium, releasing immense energy. Over time, the fusion continues up the periodic table. Helium becomes carbon, carbon becomes neon, neon becomes oxygen, and so on, each step producing heavier elements and more energy to keep the star from collapsing. But there is a limit. The final element in this fusion chain is iron. Iron is a cosmic dead end. Unlike lighter elements, fusing iron consumes energy rather than releasing it. Once a star builds up an iron core about 1.4 times the mass of the Sun, a critical mass known as the Chandrasekhar limit, it can no longer support itself. The pressure from fusion falters, and in less than a second, the core collapses. What happens next is one of the most dramatic events in the universe. The core implodes, gravity crushing protons and electrons into neutrons in a frenzy of quantum violence. The density skyrockets. The collapse is halted only when neutrons, packed together as tightly as the Pauli exclusion principle allows, push back with a force known as neutron degeneracy pressure. The core snaps into a nearly incompressible object, a neutron star, and the outer layers of the star are violently expelled in a supernova explosion, briefly outshining entire galaxies. Left behind is a sphere no wider than a major city, but with a mass greater than the Sun. Imagine compressing Mount Everest into the size of a grain of sand. Now imagine compressing the Sun into the size of Manhattan. That is a neutron star. The numbers are staggering. 1 teaspoon of neutron star matter weighs 4 billion tons. Its gravity is so immense that standing near the surface would stretch your body into a column of atoms. A human standing on a neutron star, if they could survive, would weigh over 100 billion kilograms. Even light itself struggles to escape the intense gravity, causing it to redshift, its wavelengths stretched and distorted. And yet, these stars are not merely heavy. They are dynamic, spinning, beaming, and bursting with activity. Many neutron stars are born spinning hundreds of times per second. As a result of the conservation of angular momentum, the collapsing core of the star spins faster and faster, just like a figure skater pulling in their arms. These rapidly rotating neutron stars emit beams of electromagnetic radiation from their magnetic poles. When these beams sweep across Earth, we detect them as repeating pulses of energy. These are pulsars, celestial lighthouses flashing with clockwork precision, whose regularity was once so strange that they were nicknamed LGM for Little Green Men. In fact, the first pulsar ever discovered, in 1967 by Jocelyn Bell Burnell and Anthony Hewish, appeared so regular that it briefly sparked speculation about intelligent origin. Since then, thousands of pulsars have been identified, each revealing new details about the intense environments of neutron stars. Some pulsars even exhibit glitches, momentary increases in spin rate caused by internal starquakes or interactions within their superfluid cores, events that let scientists peer into the very structure of matter under extreme conditions. Neutron stars are not just isolated phenomena. In binary systems, they can orbit other stars, white dwarfs, main sequence stars, or other neutron stars. When paired with a companion, a neutron star may siphon off material from its partner, heating up and emitting intense X-rays in the process. These X-ray binaries are cosmic powerhouses, visible across the galaxy and critical for understanding accretion physics and the behavior of matter in extreme gravitational fields. And sometimes, neutron stars collide. In 2017, the LIGO and Virgo observatories detected gravitational waves from a neutron star merger for the first time. The event, known as GW 170817, confirmed decades of theoretical predictions. Two neutron stars spiraled together, merged in a catastrophic explosion called a kilonova, and in the process, forged heavy elements like gold, platinum, and uranium, confirming that much of the universe's precious metals are created in these violent stellar deaths. This discovery was not just a triumph of observational science. It reshaped our understanding of chemical evolution in the cosmos. The matter inside neutron stars is still a frontier of physics. At their surface lies a solid crust, composed of nuclei packed in a crystalline lattice, so dense that a sugar cube of it would weigh more than all the cars on Earth. Beneath that crust lies a sea of neutron superfluid, a bizarre quantum state of matter that flows without friction, possibly interwoven with exotic particles like hyperons or kaons. And deeper still, we do not yet know. The core may contain quark matter, a fluid of up, down, and strange quarks, or other exotic states predicted by theoretical physics, but never observed directly. This makes neutron stars invaluable cosmic laboratories. They allow us to test the limits of nuclear physics, general relativity, and quantum mechanics in ways no Earth-based experiment ever could. They push equations to their breaking points and challenge our understanding of space, time, and matter. New missions, like NICER aboard the International Space Station, are measuring neutron star size and mass with extraordinary precision, helping us constrain the so-called equation of state, the relationship between pressure and density at nuclear scales. Meanwhile, continued gravitational wave observations offer entirely new ways of hearing the lives of neutron stars as they spin, quake, and collide. And yet, there's something deeply poetic about neutron stars. They are the collapsed hearts of long-dead suns, the corpses of giants that once blazed with light. In their death, they do not disappear. They shrink, condense, intensify, and in doing so, become something wholly new. They transform from spheres of searing plasma into time-keeping beacons, nuclear cores suspended in the void, whispering across the galaxy through light, gravity, and magnetism. Their story is not just one of astrophysics. It is one of cosmic recycling. Neutron stars mark the end of one cycle and the beginning of another. They are where old matter is forged into new meaning, where destruction gives birth to complexity. In their dense interiors, they carry the secrets of the early universe. In their collisions, they seed galaxies with the elements necessary for life. In the end, neutron stars remind us of something both humbling and exhilarating, that even in collapse, there is creation, even in death, transformation. They are monuments to the strange and beautiful symmetry of the cosmos, A universe where, sometimes, the smallest things contain the deepest truths.